I'm here to talk to you a bit about a automation system that I built at my previous workplace, and hopefully talk to you through a startup that I'm starting up. So a quick intro, I'm Ahmed. I've been working in biotech for 4 years now across commercial manufacturing, equipment design, and process development. But more importantly for this talk today, I've built a scale down high throughput bioprocess system, and that's kind of the topic that I'm presenting about. Volkcell is a startup that I'm starting up. It's essentially high throughput solutions for cell counting, which is a combination of a microfluidic plate and an image analysis software that enables you to do cell counting in a way that's cheap and reliable. I'll get into that more later. So I want to start this off with this equation that I strongly believe in. So combining cheap data and advanced computation will give you breakthrough products of this coming 5 to 10 years. Most industries are able to source cheap data and make these breakthrough products in the form of, I don't know, LLMs that outsource our thinking, digital twins, self-driving cars, etc. But when it comes to life science research, data sits behind tedious experiments, expensive assays, consumables, and analytic equipment. So data isn't necessarily cheap. And actually, if you want to try and do research for bioprocessing and you want to utilize the final form in which your process occurs, so say a bioreactor, and you have a set research budget, you'll find yourself constrained by the design space that you can actually cover with that form because it's very expensive to run. And so I'm actually a very big advocate for scale down. So long as it's done right, you're able to cover a big design space and understand things in a way that you couldn't before. So I guess this image that I have just illustrates how when you move down in scale, you can cover more. Yeah. So of course, when you scale down from a bioreactor down to well plates, which is what I've done and what a lot of people do, you enable yourself to do a lot of things. You enable yourself to do work like cell line discovery, media development, condition screening, process characterization, and whatnot. However, that comes with its own set of limitations. So once you move down enough in scale, you start to work with limitations of volume, and that means stuff like, oh, can I fit a sensor in this well plate? Chances are you can't. And so you have limited monitoring capacity. You have to deal with stuff like evaporation effects. And that limited volume itself limits how much you can use for offline analysis. So taking all that into account, the system that I built was a 96 well plate scale down model for suspension culture. It does all the operations you expect a scientist to do, so seeding, passaging, cell counting, getting titer, and more. And the process by which I did this is I looked through literature and I brought a couple of devices together, I built the system, and then I validated it. This is nothing crazy. A good example from the literature, which I would recommend you to look at if you're interested in this sort of work, is a paper by Roche, more specifically a scientist called Marquardt, where they scaled down all the way to 48 well plates using this automation system. Essentially, a lot of automation systems or lab automation systems are a robotic arm that communicates between different devices that do different operations. And so your incubator would be your house, and then you'd have stuff like plate readers, liquid handlers, and other specific analytical equipment that gather the data for you. So this is a good example. And what they proved is going all the way up to 48 well, they tend to get a good agreement between those conditions and the 1,000-liter bioreactor. The data they shared, however, is only 6 well and 24 well. So that was very great of them to not share that. But yeah, a good piece of paper data if you're interested in it. So me taking that, I guess, resource and other resources out there, I figured out the most important thing to scale down a bioprocess into well plates is actually mixing parameters. So establishing the ideal mixing regime gives you good oxygenation, good distribution of nutrients and metabolites, and that's the most important thing that you need to control. And a good rule of thumb for this is generally in your well plate, you want to double the height of liquid in the well. So if you start with, I don't know, X or H height of liquid in your well, you want to get that to 2H. And there is this equation out there that allows you to find the ideal mixing speed to help you achieve that. I've just detailed this here. I'm not going to go through it that much, but basically, if you want to establish ideal growth conditions in your well plates for mammalian cells, this is what you want to do. I have this slide here where I've showed me taking that equation and actually putting that into the lab and seeing what works. So you can see here that around 1,000 RPM, you get the condition where you have the best kind of mixing. This is just DMEM, by the way. But a good validation experiment is you put cells actually with your media and you do this and you stop your shaker and then you observe the very middle of your well and see if there's any cells settled. And that's just a good double verification step. So yeah, there are of course other considerations. So again, I mentioned evaporation is a big problem, and a way to get around that is you shorten your experiment cycle. So say for a bioreactor, you'd be working for maybe, I don't know, a week if you're working in batch. If you're doing fed batch, it's more than that. What you might want to consider is shortening your experiment cycle to reduce the effects of evaporation and try to still establish good differences between one condition and the other. And then, of course, when it comes to extracting data and getting metrics, you're working with a very limited volume. And so you need to ask yourself the question of what do I actually care about from this scale down model. So say if you're optimizing for titer, you might want to think, do I actually care about all these other things, or do I just care about titer? And can I get that in a way that is an endpoint measurement that can then feed an optimization model? That's something to consider. And then also you can ask yourself, can I use any non-invasive methods to not actually take samples out of my well plates and get data? And then for validation, because this system that I built was done for media development, generally what you want to see is you want to be able to establish clear differences between set conditions, and you want the scale down to match the scale up. So say, for example, I have a dilution series of a certain media. I would expect in the scale up condition, the least dilute version of that would be the one where the cells grow the best, and the most dilute is the one where it performs the worst. If I take that to my scale down, do I see the same thing? And how much time, how many days do I need to see that effect? So that is a good way of validating a system like this. I just want to finish with this final message. So I guess if you're optimizing for stuff like cell counts and viabilities in these systems, one thing that you will run into is the fact that it's very difficult to do cell counting in a way that's high throughput and cheap. And so this is what Volkcell does. I've made my own microfluidic plate that is compatible with most multimode plate readers that people have in their labs, and then a software that takes images from those plate readers and then translate those into cell counts. So this is currently in beta testing with a couple of customers, and I have an application note out. So if you would like to find out more, hear more, join the beta test, please reach out to me. I'm very approachable and I don't bite. So yeah, thank you.